Welcome to Lecture 7 of Electrical Engineering 525. In this lecture, we will move on to Chapter 5. For the moment, we're going to skip Chapter 4 in your textbook and move directly to Chapter 5, which is dealing with line sources. And for this lecture, we will look at some problems concerning uniform line sources. The problem that we'll be looking at, in fact, we'll be looking at parts A and B of problem 5.1-4. And that problem is as follows. We're asked to compute the half-power beam widths in degrees and the directivities in decibels for the following uniform line sources. The textbook has a misprint and calls it fine sources, but that's not some new thing that we haven't learned about. It's just a misprint, and it's supposed to be a line sources. So in the A part of this problem, we're looking at an 8 wavelength broadside line source. And so let's see how we would proceed in this case. If looking in Chapter 5, we see in equation 5-9 the following formula. Theta for half power is equal to the inverse cosine of plus or minus 0.443 lambda over L plus the cosine of theta naught. Now this is a pretty straightforward formula, but as we will see in the two examples that we will consider in this lecture, this formula will, there's some things about this formula that we need to pay attention to. One is how do we find theta naught, and the other one is, as we'll see in the second example, this formula sometimes gives us an answer that doesn't make sense, and so we'll need to see what happens in that case. But first of all, for the present problem, now since this is broadside, remember that we're thinking of a uniform line source here along the z-axis, and so theta equals 0 degrees would be end fire, as would theta equals 180 degrees. So theta equals 0 degrees is of course out of the top, and theta, that in the positive z direction, theta equals 180 degrees would be in the negative z direction. But those would be the end fire directions. Instead, what we want is broadside, and so theta naught in this formula is equal to 90 degrees in the case where we're looking at a broadside line source. Furthermore, we're told that this is an 8 wavelength line source, so that gives us our value for L is equal to 8 lambda. So if we stick in those values for L and theta naught into this formula for theta HP, we'll get that theta HP is equal to the inverse cosine of plus or minus 0.443 times lambda over 8 lambda plus the cosine of 90 degrees. Now, clearly the cosine of 90 degrees is 0, and so and the lambdas here in the top and bottom of this expression can be canceled, and so theta sub HP is just equal to the inverse cosine of plus or minus 0.443 over 8. And so this becomes the inverse cosine of plus or minus 0.055375. Now, when we take the upper sign, the plus sign here, the inverse cosine of plus 0.55375 is 86.826 degrees. And when we take the lower sign, the negative sign, the inverse cosine of negative 0.055375 is 93.174 degrees. So you can see how these two angles are symmetric about 90 degrees. 90 degrees is where we have our maximum, which of course is consistent with the fact that this is a broadside line source. So 90 degrees is where we have our maximum, and then we have our half power points just to the right and left of that. And just a few degrees, just 3.174 degrees to the right and 3.174 degrees to the left of 90 degrees. And so finding the half power beam width then in this case is pretty straightforward. We have that the half power beam width is equal to the absolute value of theta HP left, which is this, minus theta HP right, which is this. In fact, let me just to make sure that that's clear here, we have theta, so we'll say so theta HP left is equal to 86.826 degrees, and theta HP right is equal to 93.174 degrees. And therefore, when we take the absolute, when we use the formula that we've used several times now, that the half power beam width is the absolute value of theta HP left minus theta HP right, we get this result right here, that HP then is the absolute value of 86.826 degrees minus 93.174 degrees, or 6.348 degrees. And that is the half power beam width for this for this uniform line source, broadside line source of length 8 lambda. Now to calculate the directivity. For this is just a very straightforward calculation once you're familiar with the relevant formulas in your book. The correct formula to look at for a uniform line source broadside case is equation 5-19, and in that equation we are given that the directivity of this uniform line source, which we're denoting D sub u, the u is just to remind us is for a uniform line source. So D sub u of this uniform line source for the broadside case, and also the assumption is built into this formula now that L is much greater than lambda, which is an appropriate it's appropriate to be using that in this case since L is equal to 8 lambda. So the formula in that case is D is equal to 2L over lambda. And so when we plug in L equals 8 lambda, this will give us D sub u equals 2 times 8 lambda over lambda, or 16 lambda over lambda, which is 16. Now we were asked to find the directivity in decibels, and so we need to take 10 log of 16, and we'll get a final answer of 12.04 decibels for the directivity in this case. This is again the broadside case. So now in part B of this problem, we want to do the same calculations for the end fire case. So in this case, we assume that the source has phasing so that the main beam will be in the end fire direction rather than in the broadside direction. And that end fire direction, as we've already mentioned earlier, we'll take that to be, we could take it to be 0 degrees or 180 degrees for convenience. Let's go ahead and just take it to be 0 degrees. So once again, what we want to calculate is the half power beam width and the directivity. And as before, our formula for the half power beam width is given by theta sub HP equals inverse cosine of plus or minus 0.443 lambda over L plus cosine of theta naught. However, in this case, since we're looking in the end-fire direction, theta naught is 0 degrees rather than 90 degrees. Now still L is equal to 8 lambda. So when we plug in these values for theta naught and L into this formula, we get theta HP equals inverse cosine of plus or minus 0.443 times lambda over 8 lambda plus the cosine of 0 degrees. Now, of course, we know the cosine of 0 degrees is 1, and so we move that here, going down to the next line, we'll move that 1 from the cosine of 0 degrees. We'll put it here in the front, and so we get that the theta HP is equal to the inverse cosine of 1 plus or minus 0.443 over 8. Now think about that equation for a moment. If we take the upper sign, then we're going to, here in the parentheses, we will have a value that is greater than 1. And so that would tell us that theta HP is the inverse cosine of something greater than 1, which of course implies that the cosine of theta HP itself is greater than 1, which of course is not true for any real values of theta. So we will reject that solution. We reject the solution that we would get by using the upper sign, and we will use only the lower sign. And that's also stated right here. It says, note that no real angle has a cosine of value 1 plus 0.448 over 8. So just take the negative sign. So we're only going to look at the negative sign. So theta HP is the inverse cosine of 1 minus 0.443 over 8. And that turns out to be 19.16 degrees. But now we have only one angle, so how are we going to get the half power beam width? Well, remember now the beam maximum, we're looking in the end fire case, so the beam maximum is at 0 degrees. And so the way we interpret this 19.16 degrees is we say theta HP left is negative 19.16 degrees and theta HP right is positive 19.16 degrees. So it's going to be symmetric about our angle for the maximum, which of course is 0 degrees, and so that's how we get this minus and plus 19.6 degrees. Once we have these values for theta HP left and theta HP right, then we can use our usual formula for the half power beam width, which is the absolute value of theta HP left minus theta HP right, which in this case then would be absolute value of minus 19.16 degrees, minus 19.16 degrees, or 38.32 degrees. So as was mentioned in some of the examples in your text, when we move from broadside to end fire, the beam gets broader so that the half power beam width is now larger. This is 38.32 degrees, whereas remember in the broadside case it was 6.348 degrees. So now, what about the directivity? Well, for the end fire case, the appropriate equation to use for uniform line source is equation 5-20. And the directivity d sub u in this case, where again we're assuming that L is much greater than lambda, is d sub u equals 4L over lambda. Remember, in the broadside case, it was 2L over lambda, but in the end fire case, the appropriate equation is 4L over lambda. So be sure you're aware of that. Okay, and then in this case, then since L is equal to 8 lambda, that gives us d sub u equals 4 times 8 lambda over lambda, or 32. And once again, recalling that we were asked to report the answer in decibels, we take 10 times the log to the base 10 of 32, and we'll get 15.05 decibels. So that concludes the two examples that we want to look at for the uniform line source. And we in our test for this lecture, the first two problems will deal with finding. We'll deal with problems that are very similar to this. And so that takes care of the first two problems. Now, for the last problem on the test for this lecture, it's going to be as follows, and I just wanted to say a couple of words about this before concluding this lecture. So in that last problem, we will have something like this. We'll have a half-wave dipole, and it will be centered. The half-wave dipole is along the z-axis, and so it's pointing in the z direction, and it is centered at z equals d over 2. So it stretches from z equals d over 2 minus lambda over 4 to z equals d over 2 plus lambda over 4. And you can see then, since it's from d over 2 minus lambda over 4 to d over 2 plus lambda over 4, that gives you a total length of lambda over 2, which is consistent with this being a half-wave dipole. So we have a half-wave dipole. Oh, and by the way, you may assume here that d over 2 is greater than lambda over 4. So there's no tricks going on. This dipole is definitely, the entire length of this dipole, even the bottom of it, is definitely above the ground plane. You don't have to worry about that. So we have this half-wavelength dipole here in space above a ground plane, and you're going to be asked to find the pattern of this that we would have in the region z greater than 0 for this case. And let me just point out, in the book they have a problem similar to this, but it's with a horizontal dipole above a ground plane. The dipole is pointing in the x direction, but this one is pointing in the z direction, and which actually makes this problem easier. And so I will just leave it at that, but I'll say that, you know, the material for understanding this problem is really from lecture 6 rather than from today's lecture. So that concludes lecture 7, and good luck.